Okay, well, welcome back. Hopefully everyone is doing okay after last week's um, ANOVA chaos. Uh, I have memes again that are not related to statistics. So have some laughs. Getting catfished by food gotta be the most heartbreaking thing ever. For reals though. Go to a restaurant, smells so good, doesn't taste the same. I also found this one. Baby owls sleep face down because their heads are too heavy for their bodies. I think someone commented on this in like Instagram or something, and they were like, I am a baby owl. And then my last one, junk food expires in 5 years, health food, TikTok. And you guys know Samuel Jackson. It was just non explicit enough that I thought it would be okay to share. Okay, so those are memes. Okay, today we're basically doing the same thing we did last week. So, yay for repetition. But instead of independent samples or between subject independent variables, we're now going to have repeated measures or within subject factors, if you want to think about it that way. And then I just thought this GIF was really funny because that's probably what all of you are thinking by now. And we just keep adding tests. And you're like, no more. Okay, so let's consult our decision tree. We honestly have done more than half of the tests that we were planning on doing for the semester. So come next week, there's one more test. So that's what, November 15th. Then we have Thanksgiving break. And then there's a review week for exam 3 after Thanksgiving break. And then you have an exam, and then it's finals. So we pretty much have like a month, 4 or 5 weeks left of school. Kind of depends on when your classes actually finish, but this week we're going to be working on this red pathway. So basically the same as last week. The only thing we're changing is instead of a between subject factor, we're using a within subject factor for both if we have one independent variable as well as if we have two. So the two tests we're running this week are a one-way repeated measures ANOVA and a two-way repeated measures ANOVA. If this is too chaotic, I also have it organized this way. So study design wise, we have a single dependent variable that's ratio or interval data, a non-parametric or nominal independent variable. If we have one, we end up with a one-way ANOVA. If we have two independent variables, we end up with a two-way ANOVA, right? And then for the one-way ANOVAs, we have to have at least 3 or more variables. Two-way ANOVAs, each variable has to have 2 or more variables. In both of our tests this week, again, we have within subject independent variables. And that is how we end up with our one-way repeated measures and two-way repeated measures. All right. This slide actually is exactly the same as last week. So again, we're still looking at cause and effect. So does the independent variable have an effect on the dependent variable? Or if we're looking at levels of an independent variable, we can also say, are there significant differences between the means of each of those levels? Two-way adds the extra main effect where we look at the interaction between the independent variables. So we'll revisit that concept again. And we're still going to calculate an F-statistic. The fun thing about repeated measures is that the F-statistic is calculated differently than the independent samples. I personally think the independent samples calculations are much easier. But as you can see, this got way complicated. We added a row. But when we do within subject measures, because we are repeating the measure on the same person over and over and over again, the total variance that ends up kind of being included in our entire ANOVA, because analysis of variance, so that's where variance comes from, right? The total variance is going to be the sum of variance that comes from our condition, so the treatment that's applied or the intervention that's applied. Part of our effects come from that. Part of it comes from just individual differences. So, you know, like if we had a repeated measure of leg, or like our leg, the sides of our body, right? So if I wanted to see, are there differences between someone's like right quad strength versus their left quad strength across X number of exercises? So that would be like an example of a two-way repeated measures where we have two within subject variables. And the subject differences or the subject variances are kind of an individual thing, where it's like my right dip versus my left is something that's unique to myself. We can still look at the variance of all of our subjects as a whole, but this still is playing into the total variance that we end up seeing in people. The error portion is kind of the variance that's unaccounted for from the condition and from subject differences. So similar to last week, you guys don't have to know how to calculate the sum of squares, specifically for condition, subjects, and total, because there are certain kind of like background ways to calculate those. And I put some descriptions of them in the notes section of the PowerPoint if you downloaded that version. The only one that you will be able, or like will be tested on, well, you'll be asked questions on it in the activity this week, is the sum of squares of the error. So because the sum of squares, or our total variance, is a combination of the variance of conditions, the variance of subjects, as well as the variance of error, we can easily kind of like rearrange this equation so that we have the total sum of squares minus the conditions minus the subjects. So we isolate error by itself on one side of the equation. So you'll have to solve for that one. All of the degrees of freedom are kind of fair game for calculations. I did want to point out, just in case some people watch both of the lectures, I had misread my notes when I first recorded the other pre-recorded lecture and had mistaken my ends, or kind of like got them mixed up. So, and I revisit this in the activity pretty thoroughly, so hopefully there's not a whole lot of confusion. But little n is going to represent the total number of subjects that we collect. T will represent the number of groups. So this is kind of similar to the K variable that we used in our independent calculations last week. And then big N is going to represent the total number of data points that we have from everybody. So the degrees of freedom for the condition is very similar to a between group comparison, where we're looking at variances between group means in comparison to the mean of all of our data points. So because we're looking at group differences, we take the number of groups minus 1 for our degrees of freedom. For degrees of freedom for subjects, the sum of squares of the subjects is looking at the deviation of the mean value for each subject. So since people get measured more than once, let's say I got measured 3 times, I take the mean of those 3 values and then subtract the mean of all of the data points. So that ends up being my personal like subject variance from the mean of everybody. That's why we take the degrees of freedom as total number of subjects minus 1. When we look at the error degrees of freedom, this is basically the degrees of freedom of your condition times the degrees of freedom of your subjects. You could also think of it as the between group comparison minus the with, or multiplied by the within group comparison. So the error value is actually more similar to a within group comparison. Conditions is kind of more similar to the between group comparison if you're trying to draw lines back and forth between repeated measures ANOVA tables and independent ANOVA tables. Our total degrees of freedom is just going to be total number of data points minus 1. So that's cool. The way we calculate our mean square value is the same as last week. Bless, right? So sum of squares divided by degrees of freedom, and you just kind of like move yourself across each row. And then this week we have 2 F ratios. When you're in SPSS, you actually only get 1, and it's the between condition or between group comparison. So if, let's say, I was doing leg exercises, I don't know, and I was measuring some EMG activity in my quad, right? I want to see, do each of these exercises affect how much activity is happening in my quad? That's what this top one would actually be looking at, is the differences between the exercises. If I was looking at the subject one, that's kind of looking at my individual performances in comparison to each other instead of in like a group setting. So for the condition F ratio, it's the mean square of the conditions of this top row divided by the mean square of the error. For the subjects one, subjects divided by error. So error is always on the bottom, if that helps you remember stuff. We are going to use the whole table for our calculations this week, just so you get some practice understanding how numbers work in the table. Typically in SPSS, as well as other statistical packages, you're only going to get the conditions row and the error row. So this is true for SPSS. We'll see in the ANOVA tables, there's going to be the treatment that you enter, and then there will be an error for that treatment. And then if you have like a separate condition, that gets listed plus the error for that condition. So once we get into like the two-way ANOVAs, condition error gets stacked on top of each other for each of the independent variables and or interaction effect that we're looking at. But this is how you calculate your components of your ANOVA table. Woo! Are there any questions before I move past this slide? Okay. I'll keep an eye on the chat, just in case. The differences between our one and two-way repeated measures ANOVAs are the same as last week, and just as I said that, there was a question. The F's explain difference between the subjects. So one F, I'll skip back real quick. This F statistic for the conditions row up here, that one tells us what the differences are between the group variances. So that tells us if the conditions are significantly different from each other or not. This is the F statistic that we get a p-value for in the ANOVA tables. This F statistic we could also probably get a p-value for, but as far as meaningfulness, it's not as strongly emphasized, just because more often than not, we want to see how different treatments or different interventions compared to one another rather than how subjects compare to one another. So, but yes, the F for FS, this one does look at differences between subjects. So technically it's kind of within subjects because we're person by person, but yes, generally the idea. Okay, yeah. Difference between one and two-way ANOVAs. It's the number of independent variables, same as last week. So one-way ANOVAs have one independent variable, two-way ANOVAs have two independent variables. The only thing that's really different on this slide from last week is the fact that we have a repeated measure in here. So the naming conventions, I go through some different variations on how you can name a two-way repeated measures ANOVA in the activity. No, just kidding. It's in the part 2B lecture PowerPoint for this week. So we still need to note that we have at least two variables in the naming convention. We can either do it by saying it's a two-way, or we could use the level by level type naming convention. And then we can call it a repeated measures ANOVA, or we also refer to this as a within ANOVA. Each of the within words are kind of describing the independent variables that we have. And similarly to last week, one-way ANOVAs have a single main effect, while two-way ANOVAs have three, right? And we'll go through each of those towards the latter end of this one. Our assumptions are fairly the same as last week as well. Again, major thing that's changing is the type of independent variable. So instead of a between subject, we have within subject factors. The number of levels that are required for each type of ANOVA, though, are still the same. So one-ways require 3 or more levels, whereas two-way ANOVAs, you can have 2, but that's kind of the minimum. The other assumption that we add on, in addition to like the regular ones we usually have, is something called sphericity. And I don't know if I made this joke in the pre-recorded lecture, so I kind of feel cheesy if anybody watches both of them. But I don't know if you guys ever watched Drake and Josh, and there's like a game, like console, and it's the sphere. And Josh always walks around, he's like, it's spherical. So that's what I think of when I see sphericity. Yeah, I have a fan. Woohoo! Okay, so sphericity has nothing to do with being spherical. It's the within subject equivalent of homogeneity of variance without being homogeneity of variance. So if you guys recall, when we went through t-tests, one of our assumptions that we had for independent t-tests was homogeneity of variance. That carried over into our one and two-way independent ANOVAs. For our paired samples t-tests, we still needed to look at if the variances between our groups were relatively equal or not. And we did that by calculating difference scores. Hopefully that's ringing a bell. Okay, where we said, what's the difference between this group and this group? And then we assessed if the differences were relatively normal / equal. So sphericity is kind of building on top of that concept. We test it using Mauchly's test. All these people with these like crazy last names. It gets weirder from here, so yeah, buckle up. But the null hypothesis for sphericity / Mauchly's test is that the variances of the differences between all of the levels of the independent variable are equal. What? It's okay. I know this wording isn't the best. Usually when it comes to sphericity, because the wording gets really difficult, if you say the null hypothesis is that sphericity is assumed, I'm more than happy to accept that. If you want it in kind of like a formula type pattern, really what we're doing is we're taking, if let's say we have 3 levels of an independent variable, levels A, B, and C. What we're really doing is taking the variance of level A minus the variance of level B. That becomes a variance of the differences between 2 levels. And then we just do that for all of the other variance or difference of the variances for each pair. So we end up saying that the differences of the variances or the variances of the differences between all levels ends up being relatively equal. Yeah. Like I said, if you just want to say sphericity is assumed or sphericity is violated, that's totally fine. We do get a p-value for Mauchly's test, similar to homogeneity of variance. And the way that we interpret the p-value is same as it has been all semester. So if we have a p-value greater than 0.05, we accept the null hypothesis that the variances of the differences between all the levels of our independent variable are equal. Therefore, we have met sphericity. So there are certain, if you thought last week was rough, I apologize, this week is worse. The nice thing is it's the same pathway for both one-way and two-way. But there are different rows that you can read in the ANOVA table based on if you have met or violated Mauchly's test. So if we've met Mauchly's test and we assume sphericity, we read the sphericity assumed row in the ANOVA table. If we violate sphericity, or we get a p-value less than 0.05, so in that case, we're arguing the variances of the differences between all levels of the independent variable are not equal, then we have to kind of consult different parts of our output. So in this case, we have like Mauchly's test on the left side of the table, and then we have these epsilon values and some adjustment values that they work with the degrees of freedom so that our variances get more equal. But there's this thing called the greenhouse geyser adjustment. Told you the last names get weirder. But we look at an epsilon value. Epsilon is just a Greek letter that was assigned to this value that gets calculated for us. But we look at the epsilon value in the greenhouse geyser box. And then there are certain criteria that help us determine if we use that greenhouse geyser adjustment versus using a different adjustment. And I go more in depth in this when we go through the actual output examples. I just have it here for redundancy. The actual interpretation of all of these blue boxes, though, is the same. So once we figure out what row we're reading in the main ANOVA table, the interpretation of the p-value that comes from that adjustment or that comes from the sphericity assumed row, they're interpreted the same way. As a side note, whenever we have two levels of a within subject variable, sphericity will give us a perfect value of 1. So we do have an example of that in the activity, and we do have an example in the two-way ANOVA slides later. But when you have two levels, assume you have met sphericity. That is it. Okay. For our hypothesis testing, and feel free to put questions in the chat. I'll keep my eye on the bubble. Hypothesis testing, our null hypotheses are exactly the same as our independent ANOVAs. So yay for consistency in interpretations. One-way ANOVAs are going to be looking at the differences between at least 3 groups or 3 repeated measures. And then when we get into our significance, right, if we determine that we have a significant effect on our dependent variable, if we have to have at least 3 levels, that means there's at least one significant pair or at least one significant difference between 2 of our levels. So that's when we look at our pairwise comparisons or our post-hoc tests. The way we interpret those tests are exactly the same as how we did last week. So we say level 1 compared to level 2. Null hypothesis is always going to argue that they are not significantly different from each other. So when we end up with p-values that are less than 0.05 for any of our pairwise comparisons, that indicates that we have a significant difference between the 2 levels that are being compared in the table. So let's say that I had a significant pair for the difference between level 1 and level 3. I could then put that into, or like plug and chug into this kind of template and say if there is a significant difference between level 1 and level 3 for whatever dependent variable I've measured. Okay, if you get a p-value greater than 0.05, then you just stick with the null hypothesis, and that's that. Okay, so the process that we go through for one-way ANOVAs is fairly similar to when we had independent samples. The process for two-way repeated measures ANOVAs is also very similar. So we're still going to have 3 main effects. We'll have one main effect for one of our independent variables, a main effect for our other independent variable, and then we have our interaction effect. So again, the main effect for each independent variable is regardless of the other. So I'm probably gonna bring this concept back when we actually have numbers to look at, because I feel like it's a little bit more of a tangible example. But if we have p-values that are less than 0.05 for our main effects, they're significant. If we have p-values that are less than 0.05 for our interaction effects, we have a significant interaction. Okay. The way that we investigate our interaction effect is going to be the same as last week. So where we look at one independent variable within the levels of another, and then vice versa. So I literally copied these from last week. All I changed was the repeated measures part, which ironically I forgot to do in the lecture video, but I do mention that I messed up. As in terms of significance, we have to look at the p-value for each of our main effects in order to determine if we have significant effects. So we consult p-values for the main effect of independent variable A. If we have a significant effect, then we look at post hocs. If we have significant p-values, that's going to tell us where the significant differences lie within the levels of this given independent variable. The process is exactly the same for independent variable B. So again, consult the p-value in the ANOVA table. If we have a significant effect, look at post hoc tests, and then we try to figure out where the significant differences are. Oh. Okay. The last thing we look at is the interaction effect. So looking at levels of A within levels of B, or vice versa, levels of B within levels of A. The interaction that we get from the ANOVA table just tells us if one of the independent variables depends on the other one. So again, I feel like these examples are usually better when we have numbers attached to them. But the formatting of your tables are going to be exactly the same as they were last week. So if things didn't click then, hopefully they click now. And if they don't click this week, you still have one more chance next week. So the concepts of two-way ANOVAs, they're gonna keep coming, unfortunately. But this is what we would have as a template for levels of A within levels of B. And then I also have the reverse of that slide for levels of B within levels of A.